Good morning, afternoon, evening, and welcome to Parallel Session Deep 1 on deep decarbonization pathways. We have 1 hour and 45 minutes, 6 15-minute segments for 10 minutes of presentation and 5 minutes of questions, I understand. And then if we are on schedule, we'll have about 15 minutes of discussion at the end. So with that said, I'd like to introduce the first speaker in the program, Gunnar LUDERER from BECCS, to give a presentation on behalf of his team. Gunnar, take it away.
Thank you. I hope you can hear me okay. I have a bit
You're
of
breaking up
here.
a little bit. You're breaking up a little bit.
So.
Okay, you're on.
Nice. So you can see the slides. I hope that the meeting controls also work, the slide controls. So I will present a scenario studies focusing on the potential of electrification. And maybe as a motivation of that, let me start with reflecting on major developments in energy systems over the last decade. And the most, like the four most important things here in my view are, first, that we've seen a tremendous decrease in renewable energy costs. So these data here shown from annual, they demonstrate about an almost 80% decrease in solar PV system costs in the US over the last 8 years, which is of course quite substantial. We also see similar rates of technological change on the demand side. So in particular, if we look into battery technologies, there also was a very quick cost decrease, and actually current numbers, they even overachieve these projections by a study that was performed in 2015. So Tesla, for example, is already hitting close to $100 per kilowatt hour in battery costs. So these are two very encouraging, important developments if we think about low carbon energy systems. On the other hand, there are also aspects that are more difficult. In particular, if you look at CCS, the development is actually, it went backwards to some extent. So these are this is data about CCS project developments over the last 10 years. And between 2010 and 2017, the pipeline of CCS plants had actually decreased. So very, very few of these planned CCS projects actually materialized. So we do see much more barriers than we had hoped for on the CCS side, on the other hand. And then, of course, if you look into bioenergy, and if you consider, for example, the IPCC special report on land that came out last year, it also shows that there are very substantial sustainability concerns about large-scale bioenergy use, especially in absence of a systematic and global governance system for the land system. So what do all these trends mean? What we did is a scenario study where we kind of extrapolated these trends looked into where this gets us. So I will present three scenarios here mostly, and the most important one is a 1.5 degree scenario, which limits the global CO2 budget to around 500 gigatons, which means that warming stays or returns to below 1.5 degrees by end of the century with a very small overshoot. Importantly, in these scenarios, we assume that biomass is limited to 100 exajoules, and also CCS is very strongly limited to 4 gigatons CO2 per year. So that's around a quarter of what we usually assume in the WEYANT model. Further assumptions are that we have continued fast innovation in wind, solar, and battery technologies. For example, for solar PV systems, there's endogenous learning, but that results in $160 per kilowatt in 2050. So another 80% reduction between now and 2050 it costs. Also that integration of renewable electricity is managed via flexibilization of demand, battery storage, and also flexible H2 generation. And then also the availability of an array of demand-side electrification technologies. What we used for that study is the WEYANT 2.1 model, an energy economy-focused integrated assessment model that on one hand has a quite detailed representation of the energy supply system, but what's important for this study is that we augmented the WEYANT system with a detailed representation of energy service demands in industry, transport, and buildings, where we go energy service by energy service and explicitly represent electrification and other opportunities. So going to the results first, economics. What we see in these scenarios, so we have this 1.5 degree scenario, also a somewhat weaker one that results in well below 2 degree stabilization. CO2 prices increase quite drastically. That's not a surprise in a 1.5 degree scenario with a very tight budget, limited CCS and very limited bioenergy. But what that also means is that we also see very substantial impacts on energy markets. So if we consider secondary energy prices, of course, we are used to a system where electricity is the most expensive secondary energy carrier, and combustible fuels are substantially cheaper. If that carbon price kicks in, we see an increase in energy prices across all energy carriers. But the interesting feature of electricity is that once the decarbonization of electricity is accomplished over the 2030s, that basically this decoupling between CO2 price and electricity price development happens. On the other hand, solids, gases, liquids continue to become much more expensive over time because of the carbon pricing. So we are very quickly transitioning into a world where electricity actually becomes the cheapest energy carrier, quite contrary to what we are used to. What are implications for the energy system? So we can, on the one hand, look at the energy demand. What that plot shows is final energy demand over the course of the 21st century. And then we have a huge blob of electric final energy demands. What's of course very interesting then is to understand what remains in terms of non-electric final energy demands. And we can go sector by sector. So for the transport sector, that's actually the most dominant part of non-electric demands that remains, around 50 exajoules of liquid fuels. And if we look into detail in the specific end users, it turns out, of course, light-duty vehicles, that's quite easy to almost completely electrify, and we've seen a lot of progress here already in some countries. Also, if you look into detail into road freight, there has been a lot of development over the last 2 years, and also the stakeholders, the manufacturers are increasingly optimistic that actually by 2040, battery electric trucks can be competitive with liquid fuel trucks in a carbon constrained world. So there as well, quite deep electrification of road freight, which actually leaves us with aviation and shipping as major activities that still rely on hydrocarbon fuels. If we look at the building sector, there an interesting trend is that there is a strong autonomous tendency or a trend towards electricity-based end users. So especially appliances, especially space cooling. But then also, if you look into space heating and water heating, there are plenty of opportunities to electrify. And it, of course, it is very beneficial once you're in a world where electricity is cheaper than other secondary energy carriers. And of course, heat pumps are also more efficient than combustion-based heating. Thirdly, industrial sector. There we see that electrification potentials are very different across sectors. Just two examples of quite important sectors. If you look at chemicals, there a large part of the energy consumed is actually a feedstock. So it needs to be carbon-based. And that's why it's much more difficult in the chemical sector to phase out fossil-based hydrocarbons. On the other hand, if you look at the steel sector, there's great potential for steel recycling because we are more and more scrap steel is accumulating. So going to electric arc furnaces and scrap-based steel making really has a very big potential there. And overall, we see quite substantial electrification rates, and also hydrogen as an opportunity for indirect electrification of process heating. So what does it mean on the supply side? Let me just quickly go through those Sankey diagrams. Currently, we are, of course, in a system based on fossil-based fuels strongly. This is what the world looks like in 2050 and 2100. I'm sorry for the small print, which might be a bit difficult here. So what we see is that electricity it gets very important in this nexus between high and cheap renewable energy supply, and then via electrification making that available for the end use side. Let me close with this slide, which compares these electrification scenarios to the other integrated assessment literature. So what's shown here is electrification shares over time. We're currently at roughly 1/5 of final energy demand that's electrified. What we see is by mid-century, we are well below 50% electrification share in the 1.5 degree scenario, and that increases to around 80%, especially if you also account for hydrogen-based indirect electrification. And then we can look into other characteristics. So these scenarios are much higher in electrification shares than pre-existing IM scenarios. They are on the high end regarding wind and solar share in electricity, but much lower in terms of fossil share and primary energy in terms of CDR. And what's also interesting is that they're well below average in terms of final energy demand, and that's because electricity is such a efficient energy carrier despite relatively high and fast-growing assumption regarding end-use service demands that we have. So conclusions, what we see is demand-side electrification is likely to have much bigger potential than previously estimated, especially if we are in a world that's limited in bioenergy and CCS. Of course, electrification could be lower if bioenergy, CCS, or other carbon dioxide renewable actually gets deployed at a much larger scale than allowed in these scenarios. But also electrification could be higher if you think about aviation, for example, or shipping, where electricity or indirect electrification via hydrogen or synthetic hydrogen-based e-fuels might play an important role. And then, of course, policies are really important. This is only the competitiveness of electricity hinges on carbon pricing. It's very important to reconsider electricity market regulation in the face of variable renewables. Infrastructure is very important, and also consumer acceptance given the rate of transformation that we see on the demand side.
Great, thanks, Gunnar. We have a couple questions from Neil Grant we can take at this point. There's a noticeable reduction in final energy demand from 2020 to 2050 in the 1.5 electric scenario, before then increasing again. What is behind these dynamics? And in a more general question, what is the balance between reductions in energy service demands and energy efficiency improvements?
Yeah, great question. So what we see is like this strong reduction in energy demand between 2020 and 2050, and that's actually the time scale at which a large part of energy services switches to to electricity, where electrification also comes with big efficiency gains, and that's in the chemical industry, heating, especially also steel making. Secondary steel making is about 4 times more efficient than primary steel making. And then in the mobility sector, there also we have a factor of 3 or 4 difference in final energy to energy service efficiency. So that's what explains this dip. After 2050, like both of these efficient modes are already electrified, so we're basically seeing affluence-based demand increases that explain the further increase in final energy demand. So much of this decrease in final energy demand is really efficiency, because we are on a more efficient conversion trajectory, and to a much lesser extent reductions in energy services, but we do have elastic energy service demands.
Great, thank you very much, Gunnar. With that point, we move on to the next talk in sequence, and that is by Rui Wang from the Ministry of Education, Key Laboratory for System Modeling, and Tsinghua University. We'll talk about retrofitting coal-fired power plants with biomass, co-firing, or CCS, for net zero carbon emissions, a plant-by-plant assessment based on GIS and a life cycle assessment framework. Rui. I'm writing to support. Oh, you're okay. Yes,
yeah.
Yes, excellent.
Yes, excellent.
Okay, yeah. Rui, take it away.
Okay. Hi, my name is Wang Rui. I'm from Tsinghua University, and my major is geography, information science. And as I am quite interested in bioenergy, so I want to combine GIS with bioenergy together. So I am more concerned about the deployment plan for bioenergy. And recently, we have done some research about, we have developed a framework, and this framework is used to do a plant level assessment. And I want to share our recently result with you. Hope you will like it. And for the first slides, as I think, as we all know, President Xi has announced that China will achieve carbon neutral by 2060s, and thermal power plants have account for around 43% of China's total emissions. So they will face a lot of pressure to reduce carbon emissions. However, I think for China's power plants, it's quite different from Europe or America. China's power plants are quite young, and they have average operating year. Their average operating year is 12 years, and their units have high efficiency, and they have advanced technology. If we just consider retire these power plants, China will face huge economic loss. So we think BECCS is a great option for these power plants. And if we combine biomass and coal together to do the co-firing and plus CCS technology, we think this power plant can achieve net zero or even negative emission in their whole life cycle. We want to consider the whole life cycle emissions. So there is a question come into our mind, is that with the increasing of biomass, at which co-firing ratio can this power plant achieve net zero? We want to identify this net zero co-firing ratio. And we also think this ratio is different for different power plants, because power plants have spatial heterogeneity. They have different installed capacity. The resources nearby them are also different. So we think this ratio is quite different. we think only plant level assessment can help us answer these questions. As we want to do this plant level assessment, we think we need tools to do a more high resolution analysis. We think GIS is a great and suitable tools for us to handle this problem. And in order to solve this problem, we develop a framework, and this framework can be divided into 3 parts. First is we need to assess biomass resources in the space, and then we need to allocate this biomasses to their targeted power plant. We need to complete the supply chain for each power plant, and then once we complete this supply chain, we can assess their carbon emissions for each power plant. And now let's see the results. First is how many resources are available. We have assessed the biomass resources in the space. We choose Hubei province as our case study in this research. Hubei province is in the middle of China, and I think you are familiar with it because Wuhan is its capital city. And the biomass in Hubei province is quite available. It has around 33 million tons biomass resources, and it can meet the demand of the power plants. There are 21 power plants in Hubei province, and their spatial distribution are shown on the graph. And some of these power plants are gathered together. This means the resources nearby them will be allocated to different power plants, and then we allocate these resources to their targeted power plants. Because this is a PDF, in my power plants there should be a gift in this graph. It should be at each ratio, each power plant will choose their potential biomass collection point. Because we divide the whole area into 10 kilometers multiplied 10 kilometers fishnet, and we consider the central point as potential biomass collection point. And then we use our supply model to help each power plant choose their biomass collection point at each co-firing ratio. So it should be a gift in the process from 10% to 100%, and each power plant should choose their potential biomass collection point, and they will have a total biomass. They will have a total number of their biomass collection point and the total transportation distance, which can be shown in this 2 heat map. With the increasing of the co-firing ratio, power plants will increase their demand, and some of the power plants cannot find enough biomass resources around them. They have to go further area to collect the biomass resources if this co-firing ratio is very high, as we can see from this heat map, like number 11 and number 17 power plants. Because their transportation distance increased dramatically, so we can see in this graph, for these 2 power plants, there is a turning point for these 2 power plants. And this gives us an implication is higher co-firing ratio doesn't always bring us better carbon reduction benefits, which means maybe not all the power plants are suitable for BECCS technology retrofit strategy. We should help each power plant find their suitable retrofit strategy, and they should have their individual co-firing ratio. So that's the first implication this graph wants to tell us. And the second idea we think we can find from this graph is that almost all these 21 power plants achieve net zero at the co-firing ratio between 40% to 50%. But we think this ratio will be different in other provinces like in Inner Mongolia or Xinjiang province in China, because in this province, this province, they will not have that much biomass resources, and the power plants in theirs are there will have a lot of power plants in this province, so the biomass cannot meet the demand of this power plant. So we think this coal-firing ratio will be larger. So that's the second implication we can see from this graph. And the third one is we group these power plants by their installed capacity. We can see even the power plant with the same installed capacity, they will also have different carbon emissions. And if we want to choose a power plant to do the retrofit strategy, we can use this data to help us to make our decision. And based on this result, we are trying to give a strategy for each power plant to choose their retrofit options. We think a small power plant should choose to do the coal-firing technology, because these power plants, if we use CCS if we add CCS technology to these power plants, it will have a lot of economic costs, and it is not that economic. So we think coal-firing options is enough for them. But for the power plants with large installed capacity and the resources nearby them are enough to meet their demand, we think they should do more. They should do more. They should do the negative emissions, so they can leave carbon space for other power plants if they are not suitable for BECCS retrofit. And that's that's only a small divisions for our power plants. We haven't considered the economic factor and so on. This results only in our discussion part. So we want to do more things in this area. We want to do a more specific and more comprehensive strategy for these power plants. And if you are interested in this and have any suggestions or comment, you can contact me by email. And if you want to know more technology, you can check this paper online. Thank you.
So thanks very much, Rui. We do have a couple of questions for you, and I may put in one for Pietro. In your study, there's a question from Alexandre Schlulo about technical constraints on individual power plants and retrofitting, having to do with various operating parameters. It seemed like you talked a little bit about that. The other question, not directly related, but partially, is did you consider increased water use, both for chemical absorption, CCS purposes, and biomass?
We haven't considered that in this research. We think that is necessary to consider, but in this research we want to solve the problem between the power plant's demand and the biomass supply. But that need to be considered in our process.
Great. Now, Pietro has answered a couple of questions within the Q&A portal, which is possible. One open question is, in your study, Pietro, did you consider different rates of phase out in different countries, which could be based presumably on either existing or announced intentions to phase out fossil fuel use?
Can you hear me?
Yes, sir.
Yes, I can.
If I could maybe share again the slides for a second, because I have, the short answer is no. we didn't do so because the scenario we did develop with the narrative is quite conservative. We try to be as realistic as possible in the in choosing where the each region would go between in the position of banning the fossil fuel. So almost all big producers, for obvious reasons, are laggards. So in our opinion, this is let's say one end of the spectrum. It is difficult to be more pessimistic than this in terms of when the countries could join this kind of treaty. And SUPOL, in which all regions are frontrunner, covers the, let's say, optimistic kind of the spectrum. Yet, no, we didn't analyze. Of course, there are a lot of variables. Also, the timing. So the year in which we decide in which we enforce the ban could, of course, have some kind of effect on the results. But yeah, as this is the first of that we know of, at least the first of its kind assessment, we wanted to give a first look and not going into excessive detail with 1,000 scenarios that could complicate a lot the reading.
Great, thank you. One last question in this segment for Rui. Could you explain a little bit about the supply chain model for allocating resources? I presume this is on the biofuel co-firing feed-in.
Yeah. Okay. In our model, we use we combine the actual transportation role into our distance. We build distance matches between the power plants and the biomass collection point, and then we use a linear program solver to help each biomass collection point find their nearest power plants, and if it can meet the demand of the power plants will choose this biomass collection point, and that's our supply model.
Great, thank you.
Yeah.
At this point, I think we should keep moving. Sergey.
Trying to upload. I can start speaking. Let me just click green right slide. Okay, I'll try. What I put on the slides is our current efforts in refining the carbon capture and storage, both in power generation, but also in so-called hard operators, so industrial side, and also negative emission technologies. What we are trying to do is to get to a little bit higher level granularity in comparison to our usual approaches. The changes at the regional level and also at the sectoral level. It's going to take a look at the 1.5 IPCC 1.5 report. You will see that in most of the approaches, unless you have ways to drastically reduce demand in the previous scenario, most of the models see a quite substantial expansion of the CCS, both combined with bioenergy or CCS on fossil fuels. Also, another point is that we need emissions at an unprecedented scale to meet the 1.5. And if you would see the slide, well, I provide some graphics which shows the required rate. Also, well, we already have seen some implications from the previous crisis. So another big question mark where we are going to end up at the other end of the COVID pandemic, because the impacts are still quite uncertain, because the slow economic growth, the impacts of the pandemic also potentially can lead to a reduction in greenhouse gases. So initially, the CCS has started in application to issues. So like 10 years ago, probably even more than that, 20 years ago, Sergey PALTSEV, who is one of the co-author of this work, was looking at well, how to apply that to the coal issues. Well, now we are moving to the application of the capture and storage on the industrial sectors and negative emissions, and we are finding that these applications are even more important to reduce the cost of meeting the targets. What is also quite important is to take a look at the granularity at the sectoral level when you are employing the CCS on the industrial sectors, because well, in different sectors it will be different rates and different costs. So what we understand where we can apply that to cement industry or iron and steel industry, and how those implications affecting the resulting pathways for reduction in emissions in the mitigation scenarios. And what we are finding that the economic costs where those options are not available is substantially higher. We are seeing almost doubling the costs if those options are not available. Another thing which we are trying to understand currently is we are trying to unpack the usual assumptions from integrated assessment models, where we are trying to better, well, that usual assumptions from models of $10 per ton of carbon dioxide removed, and we are trying to provide a little bit more granularity at the regional level, where the costs of storage and transportation are changing quite dramatically from region to region. Another option, what we are trying to understand better is the capture fraction. So most of the studies assume about 90%. And so in the mitigation, those technologies, you have substantial penalty. Those remaining emissions is close to 100% with gas. Kind of sure, kind of the currently is kind of in the power generation, CCS is kind of less and less employed in the scenarios because it seems like we are getting better and trying to understand about how to solve the intermittency issues. And so usually, in comparison to the previous analysis, now show that much higher deployment of solar and wind and intermittent technologies in combination to some kind of the energy storage solution. But CCS is still quite important in other parts of the economy for reaching the net zero targets. And this is where we see a great potential for technology. So we try to understand in terms of the how much storage is available in different regions, and that's another quite important consideration because well, in some parts of the world, well, the storage is going to be a leading factor while in other parts, the storage is quite substantial resource. So that opens the question also, what is the way for the carbon dioxide transportation from regions like South Korea, Japan, or India to the place where plenty of storage is available. And again, if we are talking about the technologies like direct air capture or biomass with CCS, so all those still require substantial amount of the biomass and substantial amount of areas, but also they require substantial storage capacity. So what we are actually seeing that by the end of the century, we are at the order of about 5 gigatons, in some scenarios 10 gigatons of the captured and stored CO2 annually. So one more time, apologies for kind of the issues we uploaded in the presentation. Hopefully that gave you some indication on main questions and main issues which we are currently considering. And again, if you're interested, please send me a message to my email address, which I provided in the chat, and I'll be more than happy to share the slides and provide you references to additional work which we are currently doing and the work in progress. So thank you very much for your attention.
Great. Thank you, Sergey, for that. Right on exactly, despite all the technical setbacks, exactly 10 minutes. We give you our Enduring Freedom Award. I don't see any questions yet in the chat box for the Q&A portal for Sergey.
Hi, everyone. My name is Jerry FUHRMAN. I'm a PhD student at the University of Virginia's Department of Engineering Systems and Environment, and today I'm going to speak to you about some of the work that my colleagues and I at UVA and Pacific Northwest National Laboratory have done on assessing the food, water, and energy implications of negative emissions technologies in meeting the ambitious climate change. So the motivation for this work is ensemble becoming increasingly reliant on future. These two figures use data from the 1.5 degree scenario database by HUFFMAN et al. And the chart on the left shows that given some goal to limit end of century warming to some acceptable level, large scale negative emissions will be needed. And this need is increasing every day and every year that we delay mitigation. The chart on the left shows that although there are a number of ways by which humans could conceivably remove CO2 from the atmosphere, IAMs typically rely on large-scale bioenergy with carbon storage, or BECCS, afforestation, and increasingly direct air capture, which could conceivably enable negative emissions at similar rates of today's positive emissions, as indicated by some of the thin lines in the lower right of the chart. This work sought to assess the food, water, and energy trade-offs of these negative emissions by, for the first time, incorporating the ability to model direct air capture into the Global Change Analysis Model, or GCAM. So direct air capture is a family of aqueous or amine-based chemical processes that can separate CO2 from ambient air, and it is receiving increasing interest from the integrated assessment modeling community, as well as by governments and fossil fuel interests. So conceptually, you can think of direct air capture as taking in some energy, financial input, or capital, and possibly some water, and separating CO2 from the air. Our work focused on an aqueous DAC process developed by the Canadian company Carbon Engineering, which requires high energy, high temperature heat provided by natural gas and has some evaporative losses of water at the air contactor. While there are, of course, other potential archetypes for DAC, which can use electricity, renewable electricity, or lower quality heat, we chose to focus on this process because it appears to be the most commercially mature to date. Additionally, we focused on DAC essentially as a waste disposal surface, storing atmospheric and combustion CO2 permanently in the geosphere. However, longer term, we hope to develop the ability to model value-added CO2 use in GCAM for applications such as hydrocarbons, long-lived products such as cement, and enhanced oil recovery. So for our scenarios, we modeled two representative CO2 emissions pathways drawn from the IPCC's 1.5 degree report. The first entails very ambitious near-term climate mitigation consistent with minimizing overshoot of the 1.5 degree C target. And then we modeled a second trajectory with more delayed mitigation that in turn requires more negative emissions later in the century to return to below 1.5 C. We modeled 3 cases for the cost and availability of DAC, one with no DAC available, one with high cost DAC, and then one with low cost DAC, featuring today's more optimistic estimates for cost and energy intensity. So here are results for somewhat of a counterfactual case if DAC is never available at large scale and we instead have to rely solely on bioenergy and afforestation activities for negative emissions. Note that these results are for the low overshoot case, as the high overshoot case was infeasible because there simply was not enough land available for negative emissions, given the constraints on lands that we imposed. Here we can see that for energy, water, land, and fertilizer, bioenergy and forestry activities have large impacts on these systems, which will be in addition to streams from population growth and economic development globally. For land in particular, bioenergy and forestry activities quickly grow to take up over 6 million kilometers squared of land area, which is a land area greater than that of 50% of the United States. Here we can see results for emissions by CO2 emissions by source and sink for cases in which DAC is and is not available. DAC begins to play a multi-gigaton scale role relatively soon after our low overshoot climate policy begins after 2020, removing approximately 3 gigatons of CO2 per year in 2035. This is equivalent to about 50% of emissions from the United States in 2019. In the higher overshoot case, DAC comes online a few years later and enables deeper negative emissions to make up for the delayed early mitigation. And you can see that in all of these cases, a lot of negative emissions are going towards simply offsetting positive emissions. Spatially, you can see where our results for where we expect DAC to take place, which to the first order generally corresponds to where there is abundant expected geologic carbon storage capacity, so places like the United States, China, Brazil, and to a lesser extent, Australia, Central Asia, and the southern cone of South America. Now, moving on to our results for food price impacts and land use, which probably got the most media attention of all of our results, we see that even with direct air capture, low-cost direct air capture available, food price increases are pretty big. And this is largely, or entirely rather, due to land competition from the remaining bioenergy and afforestation activities that still take place when DAC is available. These impacts are unfortunately especially concentrated in the global south, where we see approximately 5 to 6 times price increases in the staple food crops, corn, wheat, and rice in sub-Saharan Africa. This occurs because even with low-cost DAC, we can still expect a lot of bioenergy and afforestation to occur, with direct air capture only reducing these land impacts relative to a case in which DAC is not available by 30%, approximately. But in the no DAC case, the increase in price would be much more severe, about 11 in the sub-Saharan African regions. This reduction in food price impact is nonlinear because more food productive lands are still available to produce food when DAC is available. For water, our results were somewhat surprising as well, with the water consumption for direct air capture being on the same order as that for bioenergy crop irrigation, despite being far less water intensive per unit of negative emissions. This is because how we define water use matters. When compared to biophysical water demand or evapotranspiration, or the amount of soil moisture plus irrigation water that these plants are losing to the atmosphere, direct air capture is indeed over 10 times more water efficient than growing bioenergy crops or afforesting the area. But it's important to remember that whenever vegetation was there before, it was also undergoing evapotranspiration, and so it's really the differential value that matters. And that is much closer to that of direct air capture. when we look at withdrawals and consumption, which environmental engineers are typically, think about when considering issues of water quality and quantity, direct air capture still uses less water, but it is again far closer to bioenergy. And for these metrics, we see that with DAC available, water use either stays the same or can actually slightly increase. And this occurs because, as you can see in chart D on the lower right, a fair amount of DAC is actually going towards offsetting higher positive emissions. Finally, for energy, we can see that process heat for DAC, which is coming from natural gas, if you'll recall, grows to a substantial portion of primary energy demand, which by the end of the century could be on the order of present-day global natural gas consumption being devoted towards CO2 removal. But direct air capture enables higher consumption of energy services because people are richer, owing to the lower carbon prices, and consuming more energy, as you can see from the orange line on chart C, and this would actually be a good thing. But the implications of devoting so much energy to CO2 removal need to be considered. So in summary, meeting a 1.5 degree temperature target would be a massive challenge requiring large-scale deployments of negative emissions. Direct air capture could play a multi-gigaton scale role in mitigation, but only if the policies and incentives are put in place to actually start deploying it. Further, direct air capture can soften, but not necessarily eliminate, some of the food security, or rather the worst food security issues associated with land-intensive carbon dioxide removal. The definitions of water use really do matter. Direct air capture does reduce biophysical water demand for bioenergy and afforestation activities, but it doesn't really reduce the consumptive water use or withdrawals as much. And of course, delays in mitigation greatly increase the requirement for direct air capture and other negative emissions and their associated land and water and energy impacts. And large negative emissions deployment will be required, it appears, to offset ongoing CO2 emissions. And so if we can maximize the extent to which negative emissions are actually contributing to drawing down atmospheric CO2 levels rather than just simply allowing ongoing emissions, these could substantially reduce those trade-offs. So thank you everyone for your time, and I would be happy to take any questions, and you can see our emails below if you would like to contact us.
So very nice. Jay is now online to answer questions. I don't see any in the Q&A portal yet. It's a little bit complicated because we have multiple questions for multiple questioners. One question I could ask regarding the particular instantiation of GChem you use, is there on the water side the ability to enhance irrigation in various regions, number one, and number two, in areas where there's a danger of depleting groundwater? Is that included, or could it be included?
Yeah, that's a really good question. So the version of GChem that we use does have kind of endogenous water markets, and so it is, I believe, at the river basin, large river basin level. And so yes, we do have the ability to model like irrigated versus rain-fed, and that's actually one of the reasons for some of our water consumption results, because a lot of crops are just rain-fed and not using irrigation, and so you would see that on the biophysical side in terms of the rain-fed water demand, but not the irrigated side in terms of consuming or withdrawing groundwater and surface water.
Okay, let me ask a question for you, which I think is an interesting one. Thanks for a great talk. In your scenarios, much of the DACs goes to enabling continued fossil fuel emissions rather than replacing BECCS with its problematic sustainability equity implications, including food prices. Did you or could you do any runs in which DACs, this is DACCS, is instead constrained to directly displace land-intensive CDR? Because you did talk about that issue as part of a more general equilibrium approach to reduce these issues. I guess this is a kind of robustness, sustainability argument, which is one you often do hear. So what's your response to that question?
Yeah, so that's a good question. I think long term that is certainly an area for ongoing research. For this particular study, we just imposed kind of global constraints on emissions, and then the model endogenously picked the carbon price, and so it shows it basically solved for basically what carbon price and then what mix of mitigation and negative emissions technologies would be the kind of least costs to meet that constraint on emissions. But yeah, certainly I think that we need to figure out ways to make in modeling and in the real world to make sure that the negative emissions that are not just allowing people to continue to emit more to address some of the sustainability concerns.
Great, thank you. We have time for a couple more questions. With the technical difficulties, we don't have as much time as we had hoped for questions, but we did get some interesting ones along the way. I have one for Gunnar that probably shouldn't take too much time. I think this was an interesting set of presentations. It would be interesting to have a bit more time to explore similarities and differences in the different pathways addressed. But so a lot of the questions I think regard, I would call them hard to reduce emissions and how you attack them. So the question here you've probably seen in the chat box are the hydrocarbons you use in your scenarios for aviation and shipping, are they fossil-based or synthetic in nature?
Great question. So indeed, we see there's this lower, or there is this lower limit of hydrocarbons demand that still remains in our scenarios. It's quite a bit lower than what we see in previous IAM scenarios. And in our scenarios, it's mostly supplied by bioenergy. There's a tiny bit of fossil-based oil that still stays in the system. For this study, we did not account for the possibility to synthesize, do synthetic hydrocarbon fuels based on renewables-based hydrogen. That's a debate that's extremely prominent now in Europe, in Germany mostly, also. But if we do, that plays a quite small role. It really depends on how tight your target is, and it of course also depends on how limited you are with your CDR. If you have a little bit of carbon dioxide removal, you'd really use that to offset this tiny bit of remaining fossil-based fuels that you need, as opposed to going this very, very hard and expensive way of doing renewables-based synthetic fuels.
Great, super. Actually, one thing I can contribute maybe to this conversation is you may have heard in California, on top of all the aggressive European-like 2030 targets, the governor just a few weeks ago announced a no more internal combustion engine fossil fuel vehicles on the road by 2045. So this is yet again another stretch scenario. There are some analyses I know about or we're involved in if people are interested in that, just to see another example. I guess most of the last 5 to 10 years, we've all been using the European program as kind of a example, with California a little bit from the previous 2020 target round. So with that said, we're right at the end of our time. I apologize for all the technical difficulties. I think the session was very good. I applaud nonetheless, I applaud the speakers for having excellent talks and actually hanging in there through some of the technical difficulties. I think we got the major results from all the studies, and the audience, which still numbers someplace between 50 and 150. I think we had up to 150 people in the session. We have 50 people online now. So to respect the poster session coming up next, I'd like to thank everybody once again and close down the session, and hope we can fix some of the technical problems by the time we get back to the live sessions tomorrow. But thank you all for powering through and doing such a great job despite the technical difficulties. So we're right at the top of the hour. So I would like to officially close the session at this point. Thank you very much, one and all.